Hello and welcome to this video presentation on the space-efficient construction of Lyndon arrays in linear time. My name is Jonas Ellert, and in the next 25 minutes I would like to show you the results of joint work with Bille, Johannes Fischer, Inge Gørtz, Florian Kurpicz, Ian Munro and Eva Rotenberg. Our paper focuses on the computation of nearest smaller suffixes, which is a problem that is best explained with a simple example. Consider the string all L's always fall down. At position 10 of the string, we have the suffix always fall down. We may ask the following question: which suffix is the first one that starts after position 10 and at the same time is lexicographically smaller than suffix 10? In our example, the suffixes starting at positions 11 to 16 are lexicographically larger than always fall down. The first suffix that is lexicographically smaller is the suffix all down at position 17. Therefore, we say that suffix 17 is the next smaller suffix, or short NSS, of suffix 10. Naturally, we might just as well ask for the previous smaller suffix, or short PSS, of suffix 10, which is the closest lexicographically smaller suffix starting before position 10. In our example, the PSS of always fall down is the suffix L's always fall down at position 4. Being able to quickly identify nearest smaller suffixes can be useful when performing more complex tasks on strings, for example when computing all runs in a string or during suffix sorting. This motivates data structures that can quickly determine PSS and NSS values. Ideally, the construction time of such a data structure should be linear in the length of the string. Also, once constructed, it should be able to output both the PSS and NSS value of any text position in constant time. There are two known approaches that satisfy these properties. The first one is to simply store two arrays containing all PSS and NSS values, which requires n log n bits per array. The second one is a more sophisticated parenthesis representation that requires only around 2n bits of space. For both representations, the previously best construction algorithms required order of n log n bits of additional working space. In our paper, we improved these bounds to a constant number of additional words for the array and order of n additional bits for the succinct representation. In this video, I will only talk about our construction algorithm for the succinct data structure. Our algorithm for the naive array representation is a simple modification thereof. The video consists of three parts. First, I will explain the succinct data structure. Then, I will show a simplified version of our construction algorithm that runs in n² time. In the last part, I will outline a selection of techniques that we use in order to achieve linear time. For the purpose of explaining the succinct data structure, we will continue using the example from the introduction. As we have seen earlier, the PSS of suffix 10 is suffix 4. We visualize this by drawing a directed edge from position 10 to position 4. Now I will add the respective edges for all other text positions. It is easy to see that the resulting structure forms a tree in which each text position is a child of its previous smaller suffix. Note that we only obtain a tree if the suffix at position 1 is lexicographically smaller than all other suffixes. Otherwise, some positions may not have a previous smaller suffix, and we obtain a forest instead. In such cases, we simply add an artificial root node in order to obtain a tree. Here you can see the so-called previous smaller suffix tree drawn in a more conventional layout. Using only basic tree operations, we can answer both previous and next smaller suffix queries. By definition, the PSS of suffix 10 is the parent of node 10. In order to also determine the NSS of suffix 10, we take a closer look at the subtree that is rooted in node 10. By definition, each descendant of node 10 represents a suffix that is lexicographically larger than suffix 10. Since node 17 is the first one that is not a descendant, it must represent a suffix that is lexicographically smaller than suffix 10. Therefore, 17 is the NSS of 10. In general, the NSS of any suffix I can be retrieved as I plus the size of the subtree that is rooted in I. It remains to be shown how to encode the PSS tree in a space-aware manner, while maintaining constant time parent and subtree size operations. This can be achieved by storing the PSS tree as a balanced parenthesis sequence, or short BPS. A simple way of obtaining the sequence is to perform a pre-order traversal on the tree, writing an opening parenthesis whenever we walk down an edge, and a closing parenthesis whenever we walk up an edge. We will now execute a few steps of the traversal, just to get a better understanding of the parenthesis sequence. We start at the root node 1, and initially the BPS contains only the opening parenthesis that belongs to node 1. Then we start traversing the tree by following the edge from node 1 to node 2, which means that we have to append an opening parenthesis to the BPS. Since node 2 is a leaf, we immediately return and append a closing parenthesis. Node 3 is also a leaf, and we again append an opening and a closing parenthesis. Let us look at the next 3 steps. We walk down twice and up once. Therefore, we appended 2 opening and 1 closing parentheses. Once we complete the traversal, we have a sequence of length 2n, and the opening parentheses directly correspond to the nodes in the original order. For example, the 10th opening parenthesis corresponds to node 10. Since each parenthesis can be encoded in a single bit, the entire BPS requires only 2n bits. However, the BPS itself does not support fast tree operations. Therefore, once we have computed the BPS, we transform it into a more sophisticated representation that is only a tiny bit larger. This representation can be computed from the BPS in linear time, using linear working space, and most importantly, it allows constant time parent and subtree size operations. We have seen how to encode nearest smaller suffixes using the balanced parenthesis sequence of the previous smaller suffix tree. In the next part of the video, I will explain how to directly compute the parenthesis sequence from the input string. Before going into detail, I want to point out an important property that our algorithm exploits. When drawn underneath the text, previous smaller suffix edges do not intersect, which means that a situation like the one displayed here is impossible. The left edge implies that all suffixes starting between positions 1 and 7 are lexicographically larger than suffix 7. In particular, this also means that suffix 7 is smaller than suffix 3. On the other hand, the right edge implies that all suffixes starting between positions 3 and 10 are lexicographically larger than suffix 3. In particular, this also means that suffix 3 is smaller than suffix 7. Because of this contradiction, the edges cannot intersect. Now we have the necessary knowledge to understand our construction algorithm. It follows a very simple strategy. We process the text positions one at a time and in left to right order. Processing an index I means that we first compute the index j of its previous smaller suffix. Then we attach node I as a child of node j in the PSS tree. Let us look at one step of the algorithm in more detail. In this example, we have already computed the PSS values of the first 16 indices, and the next index that we have to process is index 17. Our task is to find the previous smaller suffix of suffix 17. The first position that we might consider is position 16. Clearly, the suffix fall down is lexicographically larger than the suffix all down. Therefore, 16 is not the PSS of 17, and we have to keep looking for the PSS somewhere further to the left. At this point, we can exploit the property that previous smaller suffix edges do not intersect. Since there already is this green edge from position 16 to position 13, there cannot be an edge from positions 17 to positions 14 or 15. Otherwise, the outgoing edges from positions 16 and 17 would intersect. Therefore, we follow the green edge to position 13, which is the next position at which we might find the PSS of suffix 17. Now we continue by comparing suffixes and following existing edges until we reach a suffix that is lexicographically smaller than the suffix all down. Since the suffix a's fall down at position 13 is lexicographically larger, we follow the edge to position 10. Also here, we find a suffix that is lexicographically larger, and we follow the next edge to position 4. One more time, we find a suffix that is lexicographically larger, and we follow the outgoing edge to position 1. Finally, suffix 1 is lexicographically smaller than suffix 17, and we add an edge from position 17 to position 1. We finished processing index 17. In the next step, our algorithm will process index 18 in the same way. So far, we assumed that we can just easily follow existing edges and add new edges to the tree. However, as I mentioned earlier, our algorithm directly builds the balanced parenthesis sequence of the PSS tree. Now we will repeat the example of processing index 17, but this time we actually work only with the parenthesis sequence. Our algorithm writes the sequence in an append-only manner. At the time we start processing index 17, we have written a prefix of the sequence that ends with the opening parenthesis of node 16. As we have seen, we need to be able to follow the chain of edges that begins at the last processed index. Conveniently, the known prefix of the parenthesis sequence inherently encodes this chain. The nodes that lie on the chain directly correspond to the opening parentheses for which we have not yet written the matching closing parenthesis. During the execution of the algorithm, we maintain a small support data structure on the parenthesis sequence that provides constant time access to the nodes on the chain. Now, let us see what happens when we process index 17. First, we find out that suffix 16 is lexicographically larger than suffix 17. This means that we will not have to add any further children to node 16 in the PSS tree. Therefore, we append a closing parenthesis to the BPS, which matches the opening parenthesis of node 16. After following the edge from 16 to 13, we find out that suffix 13 is also larger than suffix 17. Therefore, we append another closing parenthesis, which matches the opening parenthesis of node 13. In the next two steps, we also add closing parentheses for node 10 and for node 4. Now, the only opening parenthesis that has not been closed yet belongs to node 1. Since we find out that suffix 1 is lexicographically smaller than suffix 17, we have to attach node 17 as a child of node 1. We can reflect this change in the BPS by simply appending one opening parenthesis. In the next step, the algorithm will continue by processing index 18. Once we have processed all indices, the last parenthesis that we have written is the opening parenthesis of node 23. In order to complete the sequence, we have to append the appropriate number of closing parentheses, one for each node on the outer chain of edges. This concludes the execution of the algorithm. Now let us analyze the space and time complexity of the algorithm. The support data structure that we use for fast chain access requires a sublinear number of additional bits. Apart from that, no additional working space is needed. The execution time of the algorithm is dominated by the time needed to lexicographically compare suffixes. Every time we compare two suffixes, we append a parenthesis to the BPS immediately afterwards. Since there are two end parentheses in total, we also perform exactly two end suffix comparisons. If implemented naively, each suffix comparison takes linear time. Therefore, the total execution time of the algorithm is at most n squared. We have seen a simplified version of our construction algorithm. In the next part of the video, I will present 3 techniques that we use to improve the execution time. They are conceptually simple, but complicated in technical detail. Only by combining all techniques we achieve the desired linear time bound. In the video, I will outline the techniques on a high level, omitting technical subtleties whenever possible. Please refer to our paper for the full details. Our first technique aims to accelerate suffix comparisons by skipping unnecessary character comparisons. Say, for example, that we want to compare the suffixes all down and Ellies always fall down. In order to determine their lexicographical order, we have to scan both suffixes simultaneously from left to right, until we find the first mismatching character. We discover that the suffixes share a common prefix of length 3, which means that the suffix comparison comes at the cost of performing 3 individual character comparisons. While discovering long common prefixes is expensive, it provides useful structural information about the string. We can exploit this information during future suffix comparisons. In our example, when processing index 17, we also compared suffix 17 with suffix 16, for which we discovered a shared prefix of length 0. Then we compared it with suffix 13, for which we discovered a shared prefix of length 1. After that, we compared it with suffix 10, for which we discovered a shared prefix of length 2. And finally, we compared it with suffix 1, for which we discovered a shared prefix of length 3. You may have already noticed that if we consider the suffix comparisons in chronological order, the shared prefixes are non-decreasing in length. Every time we compare two suffixes, the shared prefix is at least as long as the one we discovered during the previous suffix comparison. Therefore, we can speed up suffix comparisons by simply skipping the according number of character comparisons. For example, when comparing the suffixes Ellies always fall down at position 4 and all down at position 17, we do not have to investigate the first two characters, because we already discovered a shared prefix of length 2 during the previous suffix comparison. While this technique significantly improves the execution time, processing a single index might still take a long time if there are very long common prefixes. This motivates the second technique that I want to show. Oftentimes, long common prefixes are caused by so-called runs in the input string. Here we see an example of a run. The substring ABCC repeats itself 4 times. During the execution of our algorithm, we will lexicographically compare the suffixes starting at the first and second repetition of the substring ABCC. It is easy to see that the shared prefix between these suffixes extends all the way to the end of the run. The length of the shared prefix is 12. While this makes the suffix comparison very expensive, we once again gained important structural information about the string. With our second technique, we exploit the fact that runs in the string induce isomorphic structures in the PSS tree. In particular, a run in the string directly implies a run in the balanced parenthesis sequence. Now we will see how our algorithm exploits this fact. Assume that we just finished processing index 5. Since the repeating substring has length 4, the repeating isomorphic structure in the PSS tree consists of 4 edges. Performing the run extension is as simple as taking the last 4 edges that we have written and appending a copy of them underneath each repetition of the repeating substring. The exception from this is the last repetition of the substring, for which the isomorphism is not necessarily guaranteed. This can also be seen in our example, where the edges starting at positions 4, 8 and 12 point 2 positions to the left, while the edge starting at position 16 should point only 1 position to the left. The reason for this is that the lexicographical order of the suffixes starting in the last repetition might depend on characters that are not part of the run. In our example, the order between suffixes 15 and 16 depends on the character D at position 17. Since our algorithm directly builds the parenthesis sequence of the PSS tree, copying edges essentially means copying an already computed interval of the BPS. Because the run in our example has period 4, the BPS interval that we copy has to contain exactly the last 4 opening parentheses that we have written. After appending the copies, the algorithm would continue by processing index 14. Thus, by using the run extension, we skip the processing of 8 indices. The last technique that I want to quickly outline is very similar to the run extension. You can think of it as a generalization of the run extension that also applies outside of runs. As demonstrated here, we can still discover very long common prefixes even without a run. In this example, there is a common prefix of length 8 in a string of length 18. The obvious question to ask is if there are still some isomorphic structures in the PSS tree. Properly answering this question would go way beyond the scope of the video. The general problem is that even though there is a shared prefix of length 8, we cannot simply copy and append the last 8 edges that we have written. In our example, we can only copy the first 4 edges. The 5th edge is non-isomorphic between the two suffixes. We are not aware of any simple rule to determine the number of edges that can be copied, and generally speaking, that number can be anywhere in the range from 0 to the length of the shared prefix. In our paper, we show how to efficiently find out which edges can be copied, and also how to deal with the situation if only few edges can be copied. We prove that if only few edges can be copied, then we can perform the run extension and thus copy many additional edges immediately afterwards. I hope I could give you a conceptual understanding of our algorithm. I will conclude the presentation with a brief summary of our results. We have seen a succinct data structure that encodes previous and next smaller suffixes in around 2n bits. Our construction algorithm for this data structure takes linear time and uses only order of n bits of additional working space. In the paper, we also describe how to construct the PSS and NSS arrays using only a constant amount of additional working space. Lastly, I want to mention that we also implemented our algorithm. In practice, it is up to 10 times faster than previous algorithms, while also using significantly less memory. You can find some experimental results in the paper, and our implementation is publicly available on GitHub. If you watched this video before the ICALP 2020 digital conference event, then I am looking forward to answer your questions in the Q&A session. Otherwise, feel free to directly contact me if you have any questions or comments. Thanks for your attention and see you soon.